Okay, we move on to the second and the last presentation of this session. This is from European Union. The presentation will be made by Dr. Krepel of Switzerland on molten salt reactor related research in Switzerland.
Left, right, okay. Pointer. Actually, I would like to present the MSR research in Switzerland. I got an extra slot to present the MSR research in European Union on Wednesday, so I will focus only on Switzerland here. And before I will start the actual presentation, I would like to mention a little bit about the Swiss situation. As you may know, Switzerland is a lucky country from many aspects. One of them is the world's best energy mix. We are exclusively using nuclear power plants and hydropower plants for electricity production. Unfortunately, inspired by Germany, Swiss politicians want to improve this energy mix. And as a consequence, they would like to stop the nuclear power plants. There was a new law passing through parliament a year ago, and fortunately it's not so hard as in Germany. So the current power plants can still operate until they are safe, according to the regulator. And you can still build new power plants formally, but with every application you must pass through parliament. Parliament must decide, so it's not really promoting the build. The last important point is that research is allowed. So we can do research on advanced reactors. And this was shown a few weeks ago when Switzerland signed the prolongation of Generation 4 International Forum Agreement. And we are even thinking as a PS Polshar Institute, as a representative of Switzerland by Gen 4, that we will sign the memorandum of understanding for molten salt reactor, maybe somewhere during the next year. Another point I would like to say about Switzerland, as it was mentioned here, that the emissions and so on should be compared always per capita. I think also the research for these innovative systems should be measured per capita. And in Switzerland, it's a small country, it's 8 million people, so we surely don't have enough power to construct molten salt reactor. But we like the system and we would like to contribute. And the system should be probably built with a strong country with a national vision, which is probably not the case in Switzerland. So why we are looking on MSR at all? It's a very innovative system with multidisciplinary features. So you can have a department-level project on the nuclear energy department of PSI, and it's framework for students, for postdocs, and for alternative financing from, for instance, Swiss National Science Foundation, and so on. It may be acceptable because of its features, sustainability, and safety, and potentially it can be also cheaper. So therefore it may be acceptable by the public. And if we speak about fluorides, then you can also easily cooperate internationally. So the current status is that we have several master students working on MSR. There are 2 ongoing PhDs sponsored by Swiss National Science Foundation. Actually, it's the first time in the history that Swiss National Science Foundation pay money for nuclear research. So there is something on MSR from that point of view. Some PhDs visited PSI in the last 3 years working on MSR, and 2 scientists and 3 postdocs partly working on MSR, and 5 finance and 2 finished projects, which are more or less here. We are involved in the separation processes, European projects, Accept and Success. We have some competencies in molecular dynamics and thermochemistry using the in-house code GEMS. There are 2 Swiss National Science Foundation's PhD grants, and one of them is explicitly dedicated to small modular molten salt reactor design for low waste production. There is a kind of consortium of Swiss utilities which is supporting a project about feasibility and plausibility of innovative reactor concepts, where MSR is there with, let's say, 1/3. And then there are 2 projects dedicated to MSR safety and designing. It's EVOL, which finished a year ago, where we have an observer, and now the big European project SMFR, where we are a member of the consortium. But I will present the SMFR projects on Wednesday. So we tried to combine all these efforts, all this research to internal project, and we decided to define 4 working packages. The first one is core designing, but it should not be the main objective. We don't want to be a designer. Our main objective should be safety. But before you can evaluate safety, you need to know many things. You need to have competencies in the other 3 working packages, which are like designing the fuel behavior, so the chemistry of the fuel, and thermohydraulics and decay heat removal. And especially these 2 can be looked on design independently, so to say. If you just define the salt type, you don't need to know how is the exact design of the reactor, and you can still do some research. Even though the working package 1 is the not main objective, we have the most results at the moment in this. It is once again sponsored by the Swiss National Science Foundation, and we did already a decision that we would like to look on fluoride salts. Our main tool in this working package is equilibrium cycle procedure. We have one procedure called EQL3D, which is based on deterministic code Aranos and can simulate 3D distribution of burn-up in a core. And then 3 versions of equilibrium 0D based on either Aranos or Serpent, coupled with MATLAB. In these 2 first cases, it's coupled through reaction rates only for actinides without fission products. In the last version, the MATLAB and Serpent are coupled through the Serpent burn-up matrix, and it includes fission products. And all these routines are used to obtain an equilibrium cycle. So you simulate with fixed reprocessing scheme the reactor for more than 100 years until you reach an equilibrium fuel composition. So I would like to give you a few examples, because here we have the most results. One of them will be calculated with EQL0D. And as I said, it's a MATLAB script which takes the burn-up matrix from Serpent. It used the Chebyshev rational approximation method as Serpent, so equal method, but it couples media, so it's a multimedia coupling. This means that, for instance, this is the burn-up matrix for fuel salt, but thanks to the off-gas system, you are continuously removing some elements from the core, and they are appearing few lines lower in the matrix, for instance, for off-gas system. And you are explicitly solving these 2 matrices together. So you trace the composition of the off-gas system, inclusive decays and so on. So you can calculate, for instance, the decay heat produced by these 2 systems, salt and off-gas system. The MATLAB script is open source, so whoever has Serpent and would like to look on this routine is welcome. What I would like to show as next is a comparison of the results between EQL3D simulation and EQL0D simulation. We decided to use a square lattice with 5 centimeters edge and look for different moderation levels. So pure salt, fast MSR, up to heavily moderated thermal molten salt reactor with 5, 10, 15% of salt, like it was in MSBR. In all cases, we looked on the equilibrium fuel composition. And we evaluate the K infinity for the equilibrium fuel composition to understand why they differ. And so in the case of EQL0D, not only we change the salt content, but we have been also varying the size of the channel. So we call it heterogeneity effect. Yeah? So here you change the moderation, and here you change the heterogeneity. You can have a chart where you have salt share in the core and salt channel radius, And the EQL0D study covered all the space, and EQL3D more or less only one line, because the edge of the square was fixed to 5 centimeters. We didn't try other sizes. And what we looked on was the K infinity, so infinite multiplication factor, for the equilibrium fuel composition. The results are shown here. As you see, EQL0D provides you a surface in the space, and EQL3D only one curve. And this is more or less the reactivity excess for equilibrium fuel. So you can assume from this excess how good the core can breathe. And you can see also that there is a kind of, somebody calls it valley of death, because this reactor is running in resonance region, and you have really bad composition of the actinides. And you also see that if you increase the salt channel radius, it's improving. So one idea was like, what happens if you really go further, up to, let's say, 1 meter? And this you can see here, so it's up to 1 meter. And we found out that from, let's say, 50 or 60 centimeters of diameter, each channel starts to act as an independent reactor almost. And this was bringing us to an idea that you can combine thermal and fast spectra, because this channel is very thermalized on the periphery and very fast in the middle. And we came with a hybrid spectrum core. So let's say you have a normal fast MSR, which is just cylinder with salt and surrounded by hastelloy. And then we try to add in the middle graphite moderated lattice and zirconium hydride moderated lattice. And the idea was you will need less of fissile inventory at the beginning, and you may reduce the fluence on the wall, because the outer salt will be subcritical. We looked on it, and there are some results which can be presented. So the equilibrium K effective for this case is 1.017. If you add the graphite in the center, it's 1.028, so it's slightly better. But with zirconium, it doesn't work. The hydrogen is absorbing too many neutrons, so the equilibrium doesn't work. On the other hand, the initial load of uranium-3 was 11% in fast core, 6% in graphite moderated, and only 2% in zirconium hydride moderated. It is similar for LWR plutonium vector, where the graphite is even slightly worsening the situation, surprisingly. But zirconium hydride is really good, with 3.4% of plutonium share. What means more or less that you cannot use zirconium hydride for equilibrium, but you can use it for plutonium burning, which is the case of, I think, transatomic spin-off of MIT. And in these two cases, in this case, you cannot reduce the fluence on the wall, but in this case, you can already reduce the fluence on the wall. But unfortunately, you cannot use this for high powers, because all the energy will be produced in the central zone, so probably you cannot produce the same power as in this case. Another thing we analyzed was the reactivity breakdown in equilibrium. So following the EQL3D study, you have one line from fast MSR to thermal MSR, and we analyzed why the reactivity behaves as it behaves. And in this case, we included also chlorides to have a feeling about chloride salts. Okay, we also did some studies in 70 at PSI for chloride salts. And now the results. Okay, it's pretty heavy, but let's start with this chart. This is the K infinity curve you saw previously in the 3D surface plot for the equilibrium study. And this represents the excess of reactivity. So if you, from 2.5 neutrons you have per fission, if you subtract one for fission and another one for breeding, this is what is left. Yeah, what is the reactivity, excess reactivity which is left. And then you subtract step by step the absorption of neutrons or capture of neutrons of the isotopic vector of the equilibrium fuel. And you can see you have two local extremes. You have here fast MSR with the highest reactivity excess, and then thermal MSR somewhere here. If you thermalize the reactor more, then the graphite starts to parasitically absorb neutrons, so it has no sense. So this is, let's say, the operating point for thermal MSR, and this for fast reactor. And this is the worst case where you run it on resonances and you produce the worst vector. So those were fluorides in thorium cycle. We looked also on chlorides in thorium cycle for 2 cases, only fast spectrum with enriched chlorine 37 and natural chlorine. And as you can see, especially the enriched one is better. It has higher excess reactivity and equilibrium. Then we repeat the same study, the same 2 salts, fluorides and chlorides, but in uranium-plutonium cycle. And as it is known, you see that the fast uranium-plutonium cycle works, even in MSR, but you can forget the thermal one because the plutonium vector absorbs too much. In chlorides, it's much better. Chlorides are transparent, so the spectrum is really hard, and you get extremely high excess reactivity. So it's very appealing, but the spectrum is hard because the chlorides are transparent. So if you try to construct a reactor, thanks to the transparent salt, you need a really big reactor or blanket or something because the reactor will be otherwise too leaky. This is also one reason why we decided to focus on fluorides. Okay, since we saw that the chlorides are very nice on the cell level, we looked on the breed and burn scenario, possible breed and burn scenario, where you are removing the salt, throwing it away, replacing it with ferrous salt. So the same like you do in a traveling wave reactor, but in this case with homogeneously mixed fuel. And we were watching the net neutron excess. So in percent of neutrons you have in the system compared to the percent of fission material burn up. And these are the curves for the fluorides and chlorides and for thorium uranium cycle and uranium plutonium cycle. And you see that the only thing which really works is the chloride salt enriched with chlorine 37 in uranium plutonium cycle. And here, after 20% burn up, you became critical. So the neutron balance became neutral, and then you have excess of neutrons for a long time. The others does not work actually. Unfortunately, the thorium cycle in fluoride salts is close to be at 0 balance, but slightly below. Of course, here we should be sure that it works. So this is a theoretical study. Nobody can say that we can reach 40–50% burn up without having troubles with fission product solubility in the salt, of course. But if you apply these results to core level, we didn't succeed. The core should be extremely big, or you should go to blankets solution. One of the last examples for the working package one is recycling strategies. So we decided that we assume that if you have reprocessing unit with 25 liters per day capacity, you can use this unit to operate the reactor in a different recycling scheme. You can continuously remove the salt, or you can one per day remove 25 liters or 750 liters per every month. Or extreme case, assuming that you have a reactor of the MSFR type, you have 18 cubic meters in the core, you remove it every 2 years. And all these operations corresponds to equivalent of 25 liters per day. Just in this case, you need to have another salt which you put into the reactor, and then you have 2 years to process the previous salt. So you need to have twice the volume of the primary circuit. So we find the behavior, this time it is equilibrium cycle again. So you launch the equilibrium cycle without fission products after cleaning. And first of all, we find that the reactivity swing is positive. So the reactivity grows with burn up. It is because the thorium capture, thanks to decreasing thorium mass, is producing like plus 2.2 ppm per kilo, whereas the fission products, also because we have off-gas system, have only minus 2 ppm per kilo. So the reactivity is increasing. Other thing you can see that the average amount of fission products in this case is the best, because the salt at the end has always the same fission product content, but this case starts from 0 to the maximum, whereas the continuous case is always operated on the maximum because the salt you are removing has the same fission content amount. So basically this case is the best for breeding. So no continuous reprocessing, it has no meaning from neutronic point of view. You should do it batch-wise. Of course, you pay for this, but by double of the amount of the salt to operate the reactor. But it improves the breeding. And I think the load is disadvantaged, but other thing is since the thorium has a negative worst, you can eliminate this reactivity thing by continuously adding a little bit of thorium. Then you will have a flat reactivity thing and all the advantages from higher breeding. The last example from WP fund, we call it simplified fuel recycling. You know, there are many methods how to clean the salt, how to reprocess the salt. But all of these schemes, how to reprocess the salt, usually starts with volatilization. So you remove uranium, neptunium, or plutonium out of the salt in form of volatile hexafluorides, thanks to fluorine bubbling through the salt. So we decided to check what happens if you compare full recycling, so recycling all actinides, against if you recycle only uranium and neptunium through the volatilization, or only uranium. Yeah? And we compared these cases from the cumulative waste during 100 years of operation, starting from uranium-3 thorium mixture. And this is more or less the result in the three cases. So in the first case, where you recycle everything, those are just reprocessing losses. So for these isotopes, you have this amount of actinides after 100 years of operation. The power of the reactor was set up to 2.6 gigawatt thermal to have just 1 ton of fissile or fissioned material per year. If you recycle uranium and neptunium, then the neptunium amount is the same, but you produce suddenly in the waste much more of plutonium-8. It's like 1,200 kilos. More of plutonium-9, but less of higher actinides. If you recycle only uranium, then you have 13 or 1,400 kilos of neptunium. Twice more of plutonium-8, but much less of plutonium-9, and by almost 1 order less of other actinides. And since this is phased, we compare the radiotoxicity evolution, which is shown here. This is the case when you recycle everything. This is the case when you recycle uranium and neptunium. And it's so high because we have a lot of plutonium-8, which is decaying fast. And the third case, when you recycle only uranium, it's twice worse at the beginning because we have twice more plutonium-8. But in the middle part, which is driven by the higher actinides, it's much better. And at the end is again worse because we have much more of neptunium-7, which starts to decay roughly here because the half-life is 2 million years. So maybe chemists and proliferation experts should look on this and may choose what is the best for them. But the case when you recycle only uranium and the rest you discharge is relatively appealing. Or at least you can recycle uranium and store the rest for 10 years, wait for the decay of the uranium-2 products, and then you may reprocess it because it will be less active. Okay, so back to the project. The working package 2 is dedicated to fuel behavior at nominal and accidental conditions. We are a member of the SMOFAR project, so some of the work is in the frame of SMOFAR, but we have some expertise in molecular dynamics simulation, and we have an in-house code, GIPS Energy Minimalization Software for Thermodynamics Modeling, GEMS. And in the frame of the success reprocessing project, the Heracles database was modified for chlorides and fluorides, but for application to molten salt reactor, we still need to extend it. Some new mixing models should be included, and so on. And we hope to cooperate with ITU Karlsruhe in this direction. Just for illustration, this is the structure of the GEMS code. There is also a kernel. There is a kernel which is C++, a kernel which can be coupled with multiphysics tools. So once we will have the database, I can imagine we will couple this with a multi-physics solver, for instance, in OpenFOAM, or it's already done now for the final repositories. They use this kernel to solve the distribution in final repositories. WP3 thermohydraulics. Of course, thermohydraulics of molten salt reactor is special. Everybody knows. Mainly there is distributed decay heat, so volumetrically heated liquid. We would like to look on the volumetrically heated liquid study to find the new correlation of the heat exchange between the liquid and solid wall. But at the moment, we mostly focus on transient system behavior using trace or trace parks code, or for the core behavior using GenFOAM, which is our solver based on OpenFOAM. Again, a few examples. Those are 3 master theses finished this year and last year. So using trace parks, we have been simulating MSRE core. Using just trace, we looked on the heat exchanger options, so shell and tube and printed circuit. It showed up that the printed circuit is a very good option. And using the EQL0D, which is more like for the fuel cycle, we have been evaluating the decay heat release in fuel salt and in off-gas system, and it's a function of the removal rate, so of the intensity of, let's say, helium sparging or bubbling through the salt against the burn-up. So you start here with fresh fuel, and with the increasing burn-up, the decay heat content is changing, and of course with the removal rate. If you have very fast removal rate, you have a low decay in the core but high in the off-gas system. So this is thanks to the coupled matrix. You can follow both systems. And for the core, for the detailed core analysis, we have developed GenFOAM solver. It was developed on for the sodium fast reactor, but it already includes the delay neutron drift model for MSR, so it's applicable. And it solves more or less 3 or 4 different physics. There is neutronics, so multi-group time-dependent diffusion on the unstructured mesh, which you select. Cores, using porous media or fine, using CFD, mesh thermohydraulics, subscale field temperature field, and thermal mechanics. So you can simulate expansions. And for instance, in this case, where you have fast reactor with assemblies, it allows to simulate expansion of each assembly separately. So you have really deformed mesh after all. And here you see the coding for the GenFOAM. So the equations which are solved more or less. So this is also kind of solver we have. It is based on open source code, and we are ready to share if somebody is interested. The last working package, there is not much to say now because we need inputs from the others, so it will come later. But what is already there in the frame of the SMFR project, we would like to do simplified PSA level 3. So looking on what happens if you have let's say illibic release, how these let's say component will get out from the salt and distribute around the power plant in case. Okay, I think that's all from my side. Thank you very much.
Thank you. We have time for just one question if there is. Anyone?
Okay.
Yes.
In the slides for WP3, you have said some implicit coupling. Can you elaborate a little bit on that?
Which one? Yeah. Sorry, can you repeat, please, the WP3?
Yeah, in the WP3, implicit coupling you have mentioned.
Yeah.
The bullet. Can you elaborate a little bit more on that?
I'm not the main author, but I was sitting in the office with the main author. So you have 3 independent unstructured meshes for the 3 different physics, and more or less you asked the OpenFOAM to solve these three equation explicitly coupled. I can give you. You have here the sorry. You have here the reference. It's very recent paper. So either you can find it in this reference. You will get the handouts later probably. It's Fiorina Carlo. You can find it in this reference, or you can contact him. He's the main author, and he's also the contact person for this tool. Yeah.
Okay. One more question, if there is interest.
Okay.
Yeah.
When you said reprocessing of the fission products, did you mean only xenon and krypton?
In the off-gas system, we simulate that xenon and krypton is surely removed, but I think not only that, also surely molybdenum is removed, and maybe there are a few others. But this we didn't calculate or simulate this. We just based it on the Oak Ridge reports. So.
And the other aspect about recycling, you would recommend that you should recycle all the actinides.
Based on these results, I would recommend that if you have molten salt spent fuel, I would use volatilization to remove uranium, and the rest, which has no uranium-2, but has still the daughter of uranium-2, thorium-228. So, and the half-life is 2 years. So if you wait 10 years, then you may reprocess the salt later. But you don't hurry, because what is inside of the salt is not so valuable. There is no uranium. You have a lot of thorium, so you don't care about thorium. You don't care about neptunium.
But you have to store all these salts for a long
Yeah, so
time.
you can recycle uranium with volatilization as fast as possible, and the rest can wait 20 years. Or can be disposed. It depends.
Okay, I think we must close now. And let me thank Dr. Krepel for an interesting presentation. And please accept a memento.